Let's take a look at number 3 here. Which of the following correctly describes the changes in energy for a roller coaster car as it rolls down a hill? Now remember, there's 2 types of energy. There's the kinetic energy and the potential energy. Kinetic energy is the energy of what?
Kinetic energy is movement.
Energy of movement. So if you've got kinetic energy, you're moving in some way, shape, or form. Potential energy is a standing still. It's the stored energy. So remember the example I gave you way back when was the roller coaster. At the top of the hill, you've got all potential energy. But as soon as you start going down the hill on the roller coaster, that potential energy is being transformed into kinetic energy. So what's this? No. So which of the following correctly describes the change in energy for a roller coaster as it rolls down a hill? So as we're going down, top of the hill we've got potential. And as we move down, we're going to be changing that potential into kinetic. So that is A. Kinetic energy increases and potential energy decreases. Number 4. A juggler is juggling 4 beanbags. When does each beanbag have the greatest potential energy with respect to the floor? What do you think, Gus? Greatest potential energy with respect to the floor. Okay, so when is it sitting still if he's juggling it? When it's in his hand? Okay. Right. When it gets to the apex of the throw, right up here at the top, right before it begins to fall. So this is D. Or no, not D, I'm sorry, C. When it reaches its highest point. I can't read. All right, any questions on these 2? All right, any questions on these 2, guys?
Can I call on what? A and C.
All right. I can fix that.
No, you can't. Just stop.
All right. Now, we're going to move into a not a new topic per se, but kind of a side branch of the topic we've been discussing. Now, what we're going to look at today, is we're going to look at static electricity. Static electricity. And what was that? We're going to cover static electricity today, and then we'll look at some magnetism stuff a little bit later. Yes.
So is static electricity?
Yeah. All right, so static electricity. We got some. All right, so static electricity. We've all seen static electricity. We know what static electricity is. Static electricity is that thing when you're like running through the house real quick and you go and like touch somebody, it goes pa-chow! Kind of like Lightning McQueen on the front car bumper. Pow! Or whatever it is, ka-chow or...
Get out the way so I can take
Yeah. Static electricity, that's what it is. And you know what's kind of crazy is one time I was it was in the wintertime, and I just gotten out of my truck, so I had my keys in my hand, and went to put the key in the doorknob to unlock it to go in the house, and right as I got close to the doorknob, the electricity actually arced between the key and the doorknob. So static electricity. Arc, A-R-C. That's what it's called. An arc is when the electricity travels from one object to another. That little lightning boltish looking thing. Word of the day. Yeah, saw a spark. Or an arc. Now amber, that's a stone that will conduct electricity. And electron here, I know it's spelled a little bit differently, but that's the Greek word from amber. And again, that's where we get the word electron. And again, that's where we get our current word electron from. Now we have this guy named Thales or something like that. He was a Greek philosopher. And what he did is he took a piece of wool. This Greek philosopher, he took a piece of wool, rubbed it on this amber stone, and then it conducted electricity. He took the electrons from the amber and put them into the wool. Now he thought this was just something unique for amber only, which that's not the case. We now know that there are many things that will conduct electricity. And remember, what is exactly electricity? Electricity is nothing more than a exchange of charge. Usually, that's talking about exchanging of electrons. So when Thales, however you say that Greek word, did this, what was he actually doing? Well, what he was doing is he was taking and exchanging electrons between the wool and the amber. Most likely, he was pulling electrons out of the amber and into the wool. All right, any questions on the first ever electric experiment? No, that was Demetrius over here. All right, static electricity. Now there are two types of electricity, static or stationary. Again, the one that you're probably most familiar with is the static, because that's the one that gives you shocking experiences all the time. And what was funny about that? Wow. Now, with static electricity, what happens is that electricity stays put on the object that it's produced on. So whether it's your foot rubbing against the carpet, stays on the bottom of your foot, what have you. Usually these things, static electricity is produced by friction or rubbing some sort of object together. Now, a couple weeks ago we did the balloon, or we talked about the balloon rubbing against somebody's hair and then it can stick to the wall. And we determined that, yes, Josh. And then it stuck to the wall. It stuck to the wall because of the static electricity. But where did the static electricity come from? From the friction between the hair and the balloon. Now, electricity flows in a current, or what we call current. And current is just the electricity flowing down the conductor. And remember what a conductor is. A conductor is just something that will allow electricity to travel through it. Again, we talked about the copper wiring in a house. That would be the conductor. That's what allows the electricity to flow through. All right? Static or stationary? We're talking about the static.
outside free all the same.
Yeah, it was on the wood.
All right, here we go. Continue with static electricity. Now, apparently, or not apparently, there are two forms of static electricity. Now, both of these were discovered by Benjamin Franklin. Remember that kite and the key experiment? I think that was a shocking experience as well. But he discovered... Again, so two apparent forms discovered by Benjamin Franklin, one of them negative and one of them positive. Now, if we have a negative static electricity, what happens is the electrons are pulled off the atoms. And once they're pulled off of those atoms, then they congregate in a certain area. Now, so that's the one side of it. The other side of it is the positive static electricity. The positive static electricity is all of the protons that are left behind. The protons that are left behind when those electrons are removed. Now, the key with the positive static electricity is that it does not actually flow. It stays right where it's at. The negative electricity, it can move. Positive static electricity stays exactly where it's at. So again, it does not actually flow in solids, but it can be dissolved in water. So if you got some positive electricity and you want to get rid of it, toss it in the bathtub. All right. Any questions here? All right.
Wait, no, go back.
All right. Now, most substances. One more word.
Water. What? There you go.
Now, most substances in their normal state are neutral. All right, so most substances are neutral. Most substances are neutral. Again, that means they are neither positive nor negative. Positive nor negative. So that's going to be neutral. If a substance is neutral, it's going to have the same numbers of protons and electrons. If it's neutral, it's going to have the same protons and electrons. Remember, protons are positive, electrons are negative. Now, what happens though but what happens is we have a phenomenon called shielding. And what shielding does is shielding allows the outermost electron to move freely, meaning that it can travel between atoms. And when it travels between atoms, that exchanges charge, i.e. exchanges electricity. And when that does that, we call that a conductor. That object that is exchanging electrons is called the conductor. And again, a conductor is nothing more than something that will allow the electrons or allow the electricity to flow between it. Most metals are considered to be good conductors. Now, I said most metals. Not all metals are going to be conductors. Not all of them. Majority of them, yes. All of them, no. There are a few that aren't. Of course, I can't think of them off the top of my head, but there are some that are not. Alright, static electricity. Now some substances are the opposite of conductors. Some substances are the opposite of conductors. Those are called insulators. Those are called insulators. Now insulators are substances that prevent or limit the electrons from moving. They're going to prevent or limit the electrons from moving. And again, we call these insulators. Now, what happens is the electrons. Now, here's how the static electricity works. You got the conductor and you got the insulator. The electricity is going to be, the static electricity is going to be caught in one of these two locations. It's going to either be holed up on the conductor or holed up in the insulator. When something that is a conductor gets close enough to something else that is a conductor, the electricity will jump. The energy will jump from conductor to conductor. Could be that that conductor is you. Could be that conductor is another piece of metal. But as that electricity builds up, it will stay there until it jumps from conductor to conductor. When it jumps, that's what we see the spark or the arc, the little kind of purplish, bluish color electricity that jumps from point A to point B. Uh-huh. Okay. First off, you're talking about different type of electricity. Okay. Second thing that you have to look at is grounding. You're closer to the ground on your knees. So it means the electricity doesn't have to flow as far. If you're on your feet, it's got to go further, so it loses some of its punch as the further it has to go. Now, the other thing you have to look at is how electrons move. Electrons always move from areas of high concentration to areas of low concentration. And that's just like anything. Everything moves from areas of high concentration to low concentration. The reason this happens is because we're trying to reach a concept called equilibrium. And remember, equilibrium is that balance between forward and reverse, left and right, high and low. And so these electrons, they flow to that area. Not only are they going to flow from high to low, but they're also going to flow to an area to where they are going to want to spread out. And if you think about it, that makes sense. Why are they going to flow to areas so they can spread out? Because they're like charges. And what do like charges do? Like charges repel one another. So they don't want to be close to one another. They want to be spread out. They want to be spread out. So electrons are going to do two things. They're going to flow from an area of higher concentration of electrons to an area of lower concentration of electrons, and they're going to try to find an area where they can spread out and fight the repulsive properties of the electrons. Now, some more things that you have to consider when talking about static electricity. You have to consider grounding. The idea of grounding is that you send the electricity into the ground. So in most places, that means you're running a wire from a certain object to the ground. If you go to the back of your house, where your meter loop is, where the electricity from the power company comes into your house, and look down at the ground right there, you will have what's called a ground rod or a grounding rod. It'll be wherever your electricity comes in at. And what this is either a copper or aluminum pole that is driven down into the ground, usually between 6 and 8 foot, and then there will be a wire attached to that pole. And that wire will come up to the meter loop. What does that do? Well, it dissipates any electricity that gets stored up. If something goes wrong in your electrical system in your house, then that electricity flows through that grounding wire into the ground. It is a safety mechanism so nobody gets hurt. And then you have what's called an electroscope. An electroscope is a device that can be used to measure the charge. There are several different varieties of electroscope. I actually have one in my pickup. It's called a voltmeter. You can test the voltage and things. You can test the ohms and things. Now, why do I have that in my truck? Because I have all kinds of nice, cool things in the toolbox in my truck. And back in the day when I was an electrician, we used that all the time. Now, let me explain. I wasn't necessarily an electrician. I worked for an electrician. What she said.
More on that would be part of it.
Yeah. I'm one of those things, new construction, I can do new construction just fine. But trying to go in and find problems, not so good at that part. I can set it up, I just can't troubleshoot. Yeah, you got a problem, call somebody else. All right, then you also have what's called a capacitor. A capacitor is an object that can be used to store the electricity. Now, most electronics are going to have some sort of capacitor. Most electronics are going to have some sort of capacitor. What that does is that takes that electricity and it stores it in there for a time at which it needs to be used at a later date. So basically what happens is, let's say we got the TV at your house and you want to turn your TV on. If you push the power button, does the TV come on immediately? No. It takes a little bit of time. Now, so if you think about the whole big picture here, it takes a lot of electricity to get the TV going, but it only takes a little bit to keep it going. Does that make sense? Just like a car, just like a truck. It takes a lot to get going, but once you get going, it pretty well evens out and everything's fine. So if you didn't have these capacitors that store some of that electricity in there, think of how long it would take your TV to turn on now. You've got hundreds of capacitors in a TV. So you've got hundreds of places that electricity are stored that help that TV power on. But if you didn't have those, the time that it takes your TV to power on would be significantly longer. All right, more about static electricity. Let's look at some lightning here. Lightning, not white lightning, lightning. Lightning is a... What was that, Terrence? Lightning...
He said not white like
Okay.
Alright, lightning is nothing more than just a huge spark. A huge static electricity discharge. Now, how does the lightning work? Again, lightning is nothing more than a large static electricity spark that forms because of friction. And what happens is the air currents cause this lightning. So as the air rises, it gets a positive charge. As the air rises, we get positive charges. Then as the rain begins to fall, as the air then falls, the charge changes back to negative. So what results is that part of the cloud is a positive charge and part of the cloud is a negative charge. And what the lightning does is it dissipates these charges between the two.
So when you get struck by lightning,
Now, so that's when you see the lightning in the cloud. So you know y'all seen there's lightning in the cloud that just kind of lights up. Then there's lightning that streaks across the sky or down to the ground. Now, to streak across the sky, now we're not just talking about different positive and negative charges within the same cloud. We're talking about whole clouds that are now positive or negatively charged. So the whole cloud becomes positive, then the whole other cloud becomes negative. Again, they're trying to repel one another. They don't want to be against one another, so they jump across the sky between clouds, and you see that lightning bolt go, "Pshaw!"
so when you get struck by lightning, what happens when you get struck by lightning? Like you just let it shoot or something?
When you get struck by lightning,
It goes like
an electrical impulse enters your body and then leaves your body through the ground.
what?
Comes in your body at one point, travels through it, goes through your feet to the ground, and then is dissipated in the ground.
Hold on, I got a question. Is this on defense?
You know what I'm saying? It's like
All right, now, continuing on with the idea of lightning. Sometimes there are other charges.
Why Mr. Franklin gets strike? He went out there like a dummy and held a key.
We're getting there.
Why? If I would have somebody there, we got struck by lightning.
Now, again, other times a charge cloud will cause the opposite charge to build up on an object. All right, so again, think about this. If the rising air has a positive charge, that means it's pulling these positive charges away from objects around it, trees, grass, what have you. So sometimes that means that those objects will build up an opposite charge. When they do, now we've got this charge gradient, and now we can have lightning strike an other object. So like a tree, a car, a person, lightning can jump from the negative cloud to the positive ground. Now what happens with lightning is it's going to try to hit the tallest object in that area, because it's going to want to dissipate itself as quickly as possible. Now, lightning rods. Lightning rods is an object that will draw electricity or draw lightning towards it. What it basically does is it's going to be the tallest object, and it's going to attract that lightning and then shoot that electricity or shoot that energy down into the ground. Not always. Okay? So they are grounded and then take the shock to the ground. So as soon as the lightning hits the lightning rod, sucks that electricity, funnels it down into the ground to where it can be safely dissipated and not harm anyone. Now again, Mr. Franklin decided to invent the lightning rod probably about the time he discovered the lightning with the kite and the key thing. Now to answer your question, Belon, why did he not get electrocuted? I don't know. I have no idea why he didn't get electrocuted, but apparently he did. All right, now, air. The atmosphere and the air around us, that will serve and can serve as an insulator. But, remember, what's the idea of an insulator? An insulator keeps the electricity in, does not, or prevents it from being discharged to another object. However, the air is not a strong insulator. More precisely, it's not a strong enough insulator to prevent the lightning. It's not a strong enough insulator to prevent the lightning. So what does this mean? Well, what it means is that sometimes even insulators can be changed to become conductors if the charge is strong enough. So if we build up enough electricity, that insulator is going to allow that electricity to flow through there. Like it or not, it's going to happen. Because the electricity will always win this war of conductor versus insulator. The electricity is always going to be dissipated. Now, the deal with the charge. When lightning hits something, the charge is only on the conducting body. So if you think about it, lightning hits your car. Why does it not hit you? Because it's only on the car. then it goes to the ground. It's not because of the tires. Now that would be a different story. All right, continuing with this idea.
Yes, sir. I'm sorry. They beat it. What are you talking about, me?
All right, now we have induction. Now, induction, very simply, the transfer of electricity across space. The transfer of electricity across space. And then we have conduction, which is the transfer of electricity down a conductor. But conduction requires that the electricity and the object are physically touching one another. And we call that the basic law of electrostatics, which says that like charges repel and opposite charges attract. So nothing really new on this slide, but some review things. New, part the induction. Again, induction, transfer of electricity across space. Conduction, transfer to a conductor physically touching itself. I mean, not itself, physically touching between the conductor and the electron. And then the basic law of electrostatic, like charges repel, opposite charges attract. All right, static electricity. Keep going. How far you got to go? if a charge, let's say this charge is uniformly dispersed over the surface of an isolated sphere. So again, you take the picture here of the pink ball. So the charge here, what this is showing you is that it's all over the surface of the sphere. Not just here, there, and everywhere, but it's all over. It's uniformly dispersed. And it will originate at the origin here in the middle, from the center of the sphere. We call that a point charge. So, again, that's called a point charge. When that charge initiates from the beginning or from the middle here, radiates out in all directions. And you've seen these guys. You've seen those little bally things where they're all going out, and then you put your hand on it, and it sucks to your hand. It's the stuff there. Yeah. So, uniformly dispersed over the surface of an isolated sphere, when it originates from the middle, is called a point charge. All right, here we go. So we've talked about this before. A capacitor, that's a device used to store electricity. Any isolated conductor can store electricity to some extent. Okay, so capacitor, again, device used to store the electricity. Any conductor is going to store electricity a little bit. Any device that's a conductor will store electricity a little bit. So it's going to be a minor capacitor. Again, capacitor will store it. Now, what happens is if we continually add charge to this conductor, we just add and add and add and add, eventually it's going to build up. And when it builds up, or what it's building up is it's building up potential electricity, kind of like potential energy. A large potential will build up. If the potential gets high enough, then we release the spark. If the conductor is insulated, so if the conductor has some sort of insulating material on it, then the potential will build up even higher. It will go higher than it would if it was non-insulated. And then it will spark. And again, that's the idea behind what we call commercial capacitors. We insulate the capacitor, fill it with electricity, more so than if it was uninsulated, and then it will spark, turning on your TV, or turning on your microwave, or turning you on. I mean, whichever you want to look at it. It will light you up. Now, commercial capacitors. Again, what's the capacitor? Capacitor is that thing that stores up the electricity. Commercial capacitors, what they do and how they make them is they place a series of metal plates in a conductor and then surround each one of those metal plates with some sort of insulating material. Again, usually this is going to be some type of rubber or plastic. Now, the area of the plates and the distance of their separation and the amount of the insulating material they have, or the character of the insulating material, meaning how much or how efficient it is at insulating, will determine the amount of charge that capacitor can hold. The more of these plates, the more insulating material, the more charge you can hold. And again, the fewer the reverse. So the larger the volts, the larger the charge, the greater potential. And we measure the potential in volts. We measure the potential in volts. And this difference is measured between the plates, the series of plates that you have on there. Now, the capacitance. The capacitance is the ratio of the charge. So, when you calculate the capacitance, the equation that you use is C equals Q divided by V. Q is the potential difference. I'm sorry, back that up. Q is the potential charge. V is the potential difference. So you got the charge divided by the difference to give you C, the capacitance. Now the unit for capacitance is the farad. F-A-R-A-D, the farad. So when we divide the ratio of the charge by the potential difference, then we get the farad, the capacitance. Now we can also have what's called a dielectric, and a dielectric is that substance that will be used to insulate the plates of the capacitor. Okay, so dielectric is a material used to insulate the plates of the capacitor. All right? Anybody have any questions here? This is where we're going to stop today.